welcome back to this last morning session of our great conference. Our first speaker, as you see, is, you don't see, but I tell you, our first speaker is Christophe Sabot from Lyon, and we will learn news about Dirichlet random walking Dirichlet environment.
Okay, thanks a lot. So, thanks first for the invitation to this great conference. So, so I'm going to talk about a specific model of random walk in a random environment. So, which is with Dirichlet environment. So it has a specific property, so that I will explain later. So what I want to explain today is a new formula for this model, which is related to some computation we did with Pierre for, in fact, that's computation related to computation for the ERW and VRGP. And in fact, what is important here is the generalization to some non-reversible version of the edge-reinforced random walk and the VRGP, which are the star VRGP, star ERW and VRGP. So that's something we did with Pierre and put on archive 2 years ago. Okay, and this new formula leads to some sufficient condition for either existence or non-existence of the invariant measure for the process view from the particle. So I will explain later. So that's related to what Balint explained, and for existence or non-existence of invariant measure for the point of the particle. Okay, the point of view of the particle. Okay, I will not maybe write everything because it's fun. Okay, that's everything. I will explain all that. Okay, and I start by defining the model. So first step is to define a random walk in. So it's non-reversible. It's model of non-reversible random walk in random environment. So it's IID random walk in random environment. So and I will take on ZD and nearest neighbor, which is not absolutely necessary, but there's no point to complicate. So what's the model? So you just to fix notation, you denote by E1 ED, that's the base of ZD. And you denote by EI plus D, it's minus EI. Okay? So you just have the, and I will use the notation of Balint, which is that N is the set of unique vector of ZD. So that's the set E1 up to E2D. Okay? So, and then to define random walk in random environment, we first need to define the environment. So that's just the set omega of all transition probability for nearest neighbor Markov chains on ZD. So that's just a set of all omega x plus E. So that's in 0, 1 ZD times the jump. And you assume, of course, that it's normalized to 1. So if you sum on all the neighbors, then you have 1, okay? And just to fix notation, if you have such an environment, then you define the quench law. starting from a point x naught, just so if you know that xn is at y, then you jump with probability omega y plus e. Okay, so that's the standard notations. And then you take on this environment set, you take the IID law on vertices. Okay, so so for each x, you pick independently the omega x plus e, and according to the same law, okay, and you denote I will denote the anil law just as the product law. The law in the environment you get like this, so it's just the product of the law. Okay, so that's the standard definition. So that's so as you know, in dimension d larger than or equal to 1, it's if you take a non-trivial law on the environment, it's non-reversible Markov chain, and that's the main difficulty of the model. So there has been okay, and last notation I will also denote by px the anil law, so which is the expectation of the quench law. Okay, so that's the standard notation. So of course you know that there have been a huge number of work on this topic. I will not review this because I will focus on the problem of the point of view of the particle. But it's still a quite open model, even though there have been a lot of results in mainly two directions. One which when you have a ballistic condition like the T condition, and the other one is for the models at weak disorder, stable work, Erwin, Mann, and so on. So the topic of today is so I will focus on the problem of the point of view of the particle. So Balint explained already what's the point of view of the particle. So what you do is that instead of looking at one fixed environment and looking at the Markov chain, then you look at the dynamical environment. So somehow you want to look at the environment from seen. So if you have your Markov chain, your random-walking random environment, start from 0, and then you have your environment omega and all the edges, directed edges. And then what you do is that you look at the displacement of the walk, and then you shift the environment to the position where the walk is at time n. Okay? So the point of view of the particle, it's the process omega n. That's a Markov process, because since you take a huge space which contains all the information about the environment, it's a Markov process. But it's a Markov process on a big space, which is the space of environment, and it's defined by omega n. So that's the shift of omega. Okay, so that's just the spatial shift of the environment. It's clear what it is. So it means that if you have tau x of omega at y plus e, it's just the environment shifted by x. Okay. So that's a Markov process on the space of environment. And so the main question I would like to consider today, so the main question which is the standard question about this problem, is whether there exists an invariant measure for this process, but which is absolutely continuous with respect to the initial law. So the question is that does there exists a measure that I will have by Q, which is absolutely continuous with respect to P, so it means that it's rho P. And which is invariant with respect to invariant for omega L. So you can write the formula for that. It means that you must have rho of omega. So if you are at position omega, it means that this environment come from shifted by minus E. So it must be equal to the sum on all of E, all the neighbors of rho shifted by minus E omega times omega minus E0. Okay, so that's the equation for rho. So why do you want to have an absolutely continuous measure? It's just because you want to get information on the initial process. If you don't ask for absolutely continuous measure, then you can take anything, and so somehow you can completely change the law of the environment, so you don't get anything interesting about the process. Okay, so the thing is that once you have this, then you can look all the almost sure result for this Q will be also almost sure result for the P. So it's important to have absolutely continuous invariant measure. Okay, so this problem, I think it goes back to Christophe. And I think this techniques goes back, I think, to Kozlov, and it has been used a lot in the case of reversible environment. It has been less used in the case of non-reversible environment. So just to relate with the talk of Balint, you see that now if you have such a rho, then you can define a divergence-free field, because if you define gamma x plus E, so you just look at the transition probability and you multiply it by rho at tau x omega, so the invariant measure at the position x for the invariant omega, then this is a divergence-free field. Okay? So then you get into the setting of Balint. And okay, so I will explain what is known on the. So in general, it's a difficult question. It's a difficult question for non-reversible environment. So I should say, in particular, in non-ballistic case, I mean, it's difficult also in ballistic case, but it's more or less, it's better understood in ballistic case. Then I will come back to that later, but in the case of, in ballistic case, so it's even more than ballistic, but it's supposed to be equivalent, but there are some results for uniformly elliptic environment. So in ballistic case, for uniformly elliptic environment. So in uniformly elliptic just means that all the omega are larger than epsilon, a constant epsilon which is positive. Okay. Then under T condition, so I don't explain what is the T condition, but that's the condition of Stillman, which played a great role in this business. So there have been, the last result is by Perret, where he somehow solved the problem in dimension larger than 2, and before that, so it 22, and before that there were result of Berger, Cohen and Rosenthal, I think. in 87. Okay, so but for okay, I will come back to that. And last thing I should say is also that this problem of the invariant measure view from the particle, it's also related to the trapping phenomena of the environment. Why? Because if you follow the environment, if you follow the Markov chains, then at some point it may find a place where it likes to stay a longer time. So if it likes to stay a longer time, which is not somehow integrable, then you see that the random environment will concentrate on the very favorable positions. So it will create, okay, the environment will be atypical view from the particle if you have large traps. Okay.
So I solve this situation, the reason about it.
Yeah. I will come back to that because, okay, I will come back. And there's also the balance case, but which is very specific, where the environment in one direction is equal to the environment, the transition probability in direction E is equal to the transition probability in direction minus E. And that's a very specific case where you have a strong constraint on the environment. And in this case, it's also known. And I will come back to that. Okay, so I want to focus on a specific model, which is the Dirichlet environment. So first, I need to explain what is the Dirichlet law. So the Dirichlet law is something very simple. That's just a ratio of gamma functions, of gamma random variable. So if you denote by alpha 1, alpha r, which are positive numbers, and then suppose that Z1, Zr, they are independent gamma random variable with parameter alpha I. Okay? And then the Dirichlet law, then you define omega I. It's just the normalized independent gamma random variable. So it's just Zi divided by Z1 plus Zr. Okay? So you see that law on the, that's a distribution on the set of probability on set of size R, because you see that sum of omega, so omega belongs to the set of normalized probability. Okay? And you can even write the density, so that's just a generalization of the beta law. And the density is proportional to the product of omega I to the power alpha I minus 1. And then you have gamma function in the product of gamma alpha I divided by gamma of the sum of the alpha I. Okay? That's just the Dirichlet. So now the Dirichlet environment, that's just a random walk in random environment with Dirichlet laws. So Dirichlet environment. So on ZD, so I will need to define it on a general graph after, but I start by the case of ZD. Then you just take, so you have a 2D direction, you have 2D edge. Of course, you want to have a law which is environment translation. So you just fix alpha 1, alpha 2D, which are positive numbers, positive reals. So these are the parameters. So this is just the parameter of the model. And so it means that each transition probability, they are so independent, I mean in X, and they are, okay, sorry, I should write, so this, I will write Dirichlet alpha 1, alpha R. So you just pick them according to the Dirichlet law with parameter alpha 1, alpha R. Okay? So that's a simple model. I mean, that's a specific law. I will explain why it's interesting to consider this one compared to the other one. Clearly, there are some things we can do are not easy to do in general. So now I need to fix a notation. So G alpha. So you see you have a weight in each direction. So you want to see the mean direction of the drift. So you just denote by D alpha. It's the sum on I equal 1 to 2D of alpha I times EI. So alpha I, EI is either the positive base or minus the positive base. Okay, so that's how somehow the direction you expect for the walk, even though it's not easy, but you will see that's the case. And then there's another aspect of this model is that this model is not uniformly elliptic, because you see from the density or from the gamma law that omega can be as close as 0 as you want. Okay, so you may create traps. So what I mean by traps, so I explain what is the smallest trap, and in fact it's the most important one. So for example, if you take just one edge, then you understand that it's not that difficult to trap the random walk on this edge. The thing is that you just need to, so you look at all the exiting vertices, and then if all the probability transition on the exiting exiting edges are close to 0, then you will spend a long time oscillating on this edge. So it will create a trap. And in fact, there's a way to measure that. And so somehow, as you will see, the strongest finite trap, they are just the edges. So in dimension 2, you have two types of edges, either the horizontal or the vertical one. And then there's a parameter kappa, which corresponds, in fact, to, you take the sum of all the weights which exit this edge, and you take the minimum one depending on the direction. Okay? So in fact, it's just 2, the sum on I equal to 2D of alpha I, minus the maximum on all direction of alpha I plus alpha J plus alpha J plus D. So these are the opposite edges. So what does it mean? For example, if you look at there, then you see that you have essentially two types. These edges, you meet them twice, and this one just once. And if you are in higher dimension, then if you take to one edge, then you have. Okay, that's what exits from this thing. Okay, so that's the sum of the weights which exit one edge, and you take the minimal one. Okay. And the thing is that this governs the strength of the trap in the following sense. Is that somehow the thing, how do you measure traps? Then you want to know what is the integrability of the exit time of this edge. So in fact, there's something which says if you take n larger or equal to 1, if you look at the expectation of the exit time, the eating, so you start at 0 and you look at the eating time of the complement of this ball to the power p, then this is finite if and only if p is smaller than kappa. So it means in any ball, finite ball, and you see that if you want to look at the exit time of the ball, then it's integrable up to kappa. Okay? Yes? Excuse me?
not definition of kappa. This one is not equal to 1.
These are the parameters, not the values.
No, that's the parameter.
But let me, so if you take, you could do the same thing in continuous time, taking the gammas as jump rates.
Yeah, in
Then
this
would you
case,
have the same phenomenon?
no, in this case, the trap are the vertices, not the edges. Because if you allow continuous time, then you can be blocked on one side.
So then this corresponding kappa would be just the sum of the alpha.
Yeah, if you take if you take the continuous time process, then it's the sum of the alpha. In fact, it's smaller because you have
Okay, fine. So
yeah, that's the okay.
it just shows the difference between continuous and if you discretize time.
Yeah, then
This is the same as looking at the continuous time, but only at the times of jump.
yes, yeah, that's the same. Okay, so I have to hurry up a bit.
Same continuous time?
Excuse me?
Up to, these for ends. Is this integral relay condition? Is this the same for continuous time with single side traps?
No, that's what binding task. Then in this case, the traps are not the edges; they are just the single points.
But even with the single points, is the heading times for boxes? And
Yes, then in this case, it's the same thing. But it means that the strongest traps, they are just the vertices instead of the edges.
This is not straightforward. This needs a proof.
No, that's not straightforward. That's not straightforward. Actually, it's Laurent Tournier, I think he proved that in first, but now in the first time. But now we have a stronger way to show that. Yeah, in fact, if you want to show that in an efficient way, then you need the mean flow, max cut, max flow, mean cut theorem. Okay, and then, okay, so now I want to state the result, the known result, before I go to the new part. So, so let me explain first that, okay, so this model, so last thing, is that in fact, why it's interesting, maybe it's not the reason why it's interesting, but that's the reason why there are some special things, is that if you look at the annealed law of this model, then that's the directed edge reinforcement moment. So it means that you put initial weights which are alpha on the edges, on the directed edges, but you reinforce just the directed edges. Okay? So that's a natural model. And the last thing is that this model was introduced by Pimentel. In fact, it was introduced for the non-directed ERW, but on trees, because there's a relation in this case. And then we considered it first with Nathaniel Henriquez a long time ago for itself. And yes. Okay, so now so let me state the two results, which are somehow old results, but the first one is, but they will be necessary to understand the rest. So directional transients. So this explains the asymptotic behavior, I mean the rough asymptotic behavior of the process. So that's something Tournier 10 years ago. And Laurent Tournier also improved that in 2013. Okay, so the result is the following. It's quite natural. In fact, it's not that easy to prove, but it uses okay. The two results I will state use a key property that we'll explain briefly later. So it says that it's not surprising in terms of behavior. It says that if d alpha is not equal to 0, then you have okay. Let's say if d alpha is equal to 0, so it means that in terms of means of the weights, then it's centered. For example, it's the isotropic case. And in this case, you are recurrent in direction. Okay? So in each direction, you oscillate. Okay? And now, if d alpha is equal to 0, is not equal to 0, then in this case, if you look at xn dot E alpha, so it means that xn goes to infinity in the direction of d alpha, and in fact, in terms of direction, you have that xn divided by its norm converges to d alpha divided by this norm. So it means that the asymptotic direction is the mean of the mean vector of the alpha. Okay, it's a computation. I don't really understand why it's true, because that's a lattice graph, so they should be influence of the lattice, but it's the case.
This tells already something about the stationary rho.
No, I don't think
yes,
so.
because the d alpha should be, so on the
Yeah.
left-hand side depends on the stationary behavior.
Yeah,
And the right-hand side is computed just locally from the origin.
I agree that,
Velocity can be zero.
yeah, but somehow you can still accelerate the process, and then the velocity is always non-zero in dimension 3 and more. Okay, but in this model, and then it means that indeed, if you take the expectation with respect to the invariant measure, if it exists, then it's in the direction of the alpha.
But the right-hand side is computed without knowledge of the invariant measure, just locally from the a priori distribution.
Well, it's the time reversal property I will explain later. Okay, so that's the first statement. And the second statement is about the invariant measure and the transients in dimension 3 and more.
Can I ask a question about what you just said? If the velocity is zero, then it cannot be. Then it's not true that the alpha is the mean of the invariant measure.
No, I agree.
It's
In
only
fact,
if the velocity is not zero.
yes. But in fact, in this case, in dimension 3 and more, if kappa is larger than 1, then there's, and even though you can accelerate the process such that you have an invariant measure, I will explain
Then
that.
the invariant measure will not be this one. It will not be the invariant measure for a single shift.
No, it will be the invariant measure. Okay, you change
Along
the.
subsequent.
You can change the time. You can make a change of time by a local function, such that you kill all finite traps. And in this case, there's positive speed. But okay. So the second result is also two results, in fact, and that's dimension 3 and more. So the first one is that for all alpha, so this is true for all alpha. In particular, it's true for the. Okay. Then the random walk in Dirichlet environment is transient, and you have a good control on the green function. So if you look at the green function at 0, 0, so the expected number of return to 0, then this is finite. The P, you have LP moment, finite LP moment for all P smaller than the kappa. So it means that somehow it's the same as looking, if you look at the integrability, it's the same as looking at finite box or infinite box. Okay? Because that's something you have for finite box. Somehow not for free, because it's not that simple, but that's essentially this one.
So the equality is different now.
Excuse me?
So here I can take P constant alpha.
Said strictly. Sorry. Yes. That's strictly. Okay, and the second statement is that if kappa is larger or equal to 1, there exists an invariant measure due from the particle which is like Q equal rho P, which is absolutely continuous with respect to P, and in fact you have information about the moment of P. So the density, the radon-Nicodim derivative has finite p moment if and only if p is smaller than kappa. That's the same. Which is not very surprising because the kappa, I mean, it's not surprising that it's this one if you think that that's only finite traps which counts, because this one governs the fact that you are trapped in a ball or at a point. Okay? So that's the result we had for the. I should hurry up a bit. Okay. So, are there questions there? No? So this was used, I will not explain how it was used, but this was used to prove a ballisticity. Because if you have that, then you can prove ballisticity if kappa is larger than 1. That's strictly. And you can also prove if kappa is smaller or equal to 1, then you can prove also a stable limit theorem. That's maybe put Vig. And okay, the problem. So in fact, you can replace the T condition by the existence of an invariant measure to prove integrability of the René-Wall time. One difficulty is that you cannot prove square integrability of the René-Wall time just from the invariant measure. So if you need to go to if you want to go to the CLT, then you need more, and that's a bit frustrating, but. Okay, with a trick of Balint, we have also a lower bound on the diffusivity. So we have something like something we wrote in the note that xn square is at least. Well, I think it's constant time n, but actually at this level it's subdiffusive. It's not subdiffusive. Well, kappa may be larger than 2. I think it's 2 or 3, I don't remember.
Then it's not this, it's this minus the mean.
Okay, I think it's the centered case.
The center.
D alpha equals 0.
Equal alpha is the same.
D alpha equals 0. That's the centered case. Okay, and in fact you can remove this condition of kappa larger than 1. But then you need to accelerate by a local function. So you have finite traps, and you say if I see a finite trap, so it's a finite, it's a function from a finite set, and then you accelerate your process depending on this, and then you can remove this condition kappa smaller than 1, bigger than 1.
But the ballisticity you have when this d alpha is not 0.
Yes.
When d alpha is not 0, right?
Yes, of course.
And the stable law holds for the displacement, you say?
That's a stable limit theorem. So it means that xn divided by n power kappa,
for kappa less than
1 over kappa, kappa less than 1.
You have that in 3 and more dimensions.
Yes, that's the result of Rémy. And in fact, I didn't say that Adrien Perel is my PhD and that just won't work. And he's looking at the stable fluctuation, but then you need more. Yes.
Did I understand correctly that you don't have CLT?
Yeah, we have CLT, but then we need more. We need to add T condition or something. We can have CLT by standard technique, so somehow it needs.
Just kappa greater than 2 and d alpha non-zero, you don't have a.
No. That's not enough because the problem is that if you have the invariant measure, then you don't have integrability of the René-Wall times. It just gives. I mean, you don't have square integrability of the René-Wall times. That's the problem. Okay, so all this property comes from a time reversal. I will briefly sketch it, and then I will come to the new formula because I see that time is running.
You have 20 minutes left.
Yeah, a bit less. So I need to go a bit faster. So the thing is that to go further, then you need to define Dirichlet environment on general graph. That's not a big deal on general graphs. So you take G, which is a directed graph, and then you put alpha E, which are positive weights, which play the role of the other one, so that's weights on the directed edges. And what you do is that you just think that you create a Markov chain on this directed graph just by picking for each I and V. Then you look at omega E. If you suppose that the origin of E is I, which are independent Dirichlet law with parameter alpha E. Okay, so it means that at each vertex, then you have some parameter alpha 1, alpha 2, alpha 3, and then you pick a Dirichlet law there for the exit probability. So it gives you a Markov chain on a finite set, on a set. And now, maybe just to, what was the key property of Dirichlet which makes things work? So a key property is that so you introduce the divergence. So be careful, it's not the divergence of the environment, it's the divergence of the weight. So you define the divergence of the weights, that's the sum. So at the vertex I in V, that's the sum of the weight which exit I minus the sum of the weights which enter I. Okay? So that's just the divergence, standard divergence on a, just you look at the weights that exist minus the weights that enter. And the result is that if you suppose that you have G, which is finite, and connected, then you denote by omega I star, which is the dual Markov chain. So it's just the Markov chain, the initial Markov chain, conjugated by the invariant measure. Okay, so that's just a time reverse Markov chain, the standard one. Okay, so it's a Markov chain which lives on the reverse graph, where you reverse the direction of all edges. And the result is the following, is that if the divergence of the weight is equal to 0, then omega star is again a Dirichlet law. With the, just you reversed all the weights of the edges. Okay? So a priori it's quite surprising, because if you look at this formula, then that's a highly correlated environment, because you correlate this by the invariant measure. So it's very special to this model. And in fact, somehow this characterizes the Dirichlet environment. So in the following sense is that if omega is an independent environment at each set, and if you suppose that the dual space is again independent at each vertex, then it's a Dirichlet with zero divergence. And that's Pudvin also proved that. That's characterized. And that's a result of Remy Pudvin. Okay, so now I want to come back. So this formula, I don't explain how it was used. Maybe I will come back to a different proof of this related more to the VRGP. So now I want to come back to the new formula. So I don't think this formula can be deduced from the time reversal, although I'm not completely sure, but I don't see how. And this formula is inspired by a computation so that's related to the H beta of Margarita yesterday and of Valentin, but I will not go into that because we can do direct proof. But the generalization that we did with Pierre. So, so a new formula. So you take again, so that in all this business, the formula are not finite graphs. So G finite, connected. And then you take 2 points, I naught, G naught, and you suppose that the divergence, okay, assume that the divergence is equal to 0. But in fact, okay, no, write it like this. The divergence is equal to delta I naught minus delta G naught. So it means that alpha is a flow from I naught to G naught with strength H. Okay, but you can think that divergence is equal to 0. H is equal to 0, okay? And then you look at two quantities. Okay, and then you take beta I naught and beta G naught for these two vertices, which are gamma random variable with parameter alpha I naught, alpha G naught. So alpha I naught is just the sum of the weight which exit I naught. Okay, just sum of the weights which exit the vertex. And you take two gamma random variables which are independent of the environment and independent together. And then you define two quantities.
And independent between them.
And independent between them, of course. Yes. Then you define two quantities. Gamma is the square root of beta I naught. And then you look at the probability. I will explain what it is, times beta G naught times the probability to go from G naught to I naught. So what is this? So this is the probability to go from I naught to G naught without going back to G naught, before going back to I naught. Okay? So it's a direct path, the probability of direct path from I naught to G naught. Not direct, but in the sense that you don't come back. Okay? That's the probability to go to G naught before going back to I naught. Okay? And the same in the reverse. And then you define exponential S. That's the same thing, but you take the ratio now. Okay? Take the ratio of the two. Then the result is that you can compute the law of this one condition on this one. So the law of S condition on gamma, then it's explicit, and in fact it's a Bessel function. It's 1 over, so that's the normalization function. So that's the modified Bessel function to gamma with parameter gamma, so that's exponential minus S, exponential minus 2 gamma cosh S. So you have an explicit formula for the law of the ratio of these two quantities, condition on the law of the product of the two quantities. Okay? So do you see the clear formula? Ah, shit, too late. Okay? So now there are two consequences of that. So for the maybe the most interesting, in fact, is the proof of that, but I'm not sure I will have time to explain it. But So then you can deduce the following result. Is that the first thing is that if you suppose that you are in dimension 2, so you come back to ZD, and you suppose that you are centered, and then you need to assume something which should be true, but I don't know how to prove. If you assume that the random walk in Dirichlet environment is recurrent, that should be true when it's centered and when it's dimension 2. Then there exists no invariant measure of view from the particle. Absolutely continuous. Okay? And then something you can prove also is that if d alpha is not equal to 0, and if you assume the T condition, which is a strong biasticity condition, then there exists invariant measure and you have that with p moment. Up to kappa. Okay? So this result somehow, this result is somehow less surprising because it's true for elliptic environment. It's not proved somehow formally because it's for elliptic environment, but it's known for, okay, this is not uniformly elliptic, but it's known for uniformly elliptic. So, the first one is
But your old result was exactly this one?
no, that's 2D,
Yeah.
that's D equal 2.
So
Okay, I stated D equal 2 because otherwise it's known and it's never. So the thing is that so it's a bit frustrating because you asked to assume that the ID is recurrent. So, but you know that if d alpha is equal to 0, then it should be recurrent, and if d alpha is not equal to 0, it should be T condition. So that's natural to conjecture that there exists an invariant measure if and only if d alpha is not equal to 0 and kappa larger than 1. And this, you can, I think, remove the kappa if you allow some acceleration by invariant measure, by the code. That's rho is the density of the, is the density. Rho p is finite if and only p is smaller. And so, okay.
But what did you say about strict electricity? You can't have it.
No, that's why I say, but I say it's not uniformity. That's why I say it's not proved. But I say it's proved for uniform. The second one is proved for uniformly elliptic.
When? For what?
But in parents.
So in
Okay.
general for uniform.
Yeah, for general but uniformly elliptic. So I said that this one is not so interesting because it's so. But the first one is so. Maybe I explain why you can deduce from this formula the first one. Yes.
Does the first one say even after a time change you will not have an
Yes, even after a time change you will
You
not.
cannot make a time
You cannot make a local time change. Okay, but this is very simple from this result. Why? Because you see that if you take a big torus, and you suppose that you're recurrent, so if you take I naught, J naught, which are far from each other, so it means that this value will be small with large probability. Okay, because it's difficult to go directly to go from I naught to J naught without going back to I naught. Okay, so this will go to 0. So it means that if gamma is small, if you look at this expression and you take, in this case, it is the case h equal to 0, so you don't have this term. So it means that this s will fluctuate a lot because gamma is small. So you have exponential minus 2 gamma cosh s. Okay, so this will fluctuate a lot. And so it means that conditionally on the fact that this gamma is small, then this s will be large. But now if you look at what is this s, that's just the ratio of the invariant measure. So that's pg naught divided by pi naught. So it means that you will have large fluctuation of the invariant measure, of the ratio of the invariant measure. But if you have a stationary invariant measure, it's recurrent, then you cannot allow large fluctuation, arbitrary large fluctuation. Is it clear? No? Yes?
How do you get that equality?
Excuse me?
It's early in the morning. How do you get the condition properties to oh, because the
That?
yeah, it's like
Well, that's the
probability.
standard formula that you can write the invariant measure as the expected number of visits of, if you normalize it to 0 at J0, the expected visit of, so that's the ratio of the invariant measure. So it means that if the probability, you have recurrence, then the probability is small, then in this case the ratio has to be large. So it means that if it's difficult to connect I0 to J0, then you have large fluctuation on the ratio of going from I0 to J0. Yes? Okay, the second part is a bit more complicated, I will not extend. So maybe if I have...
We can't go much beyond because the next talk
No,
is...
no, no, I
next
don't want,
talk
no,
is
no, no,
online.
I don't want to... That's maybe just to explain the first step of the...
So
The first step of the proof.
You have 1.5 minutes for that.
Okay. So the first step of the proof, so the key thing is to prove this formula. So that's related to computation for the VRGP. So the thing is that you have to add an extra layer of randomness. Should stop writing everything. So you take the finite graph and you take W, which are independent gamma with parameter alpha ij. And then there's a key formula that we use with Pierre to go from the star ERW to the star VRGP, is that if you look at, you want to construct a field Uj such that it's rooted at 0 at I0, and then you look at this formula. That's the sum on Ij, all the edges, Wij exponential of Uj minus Ui. And you normalize it. So that's a distribution on function on the vertices. And if you do that, so it means that conditionally on W, you pick U like this. Okay? Then the result is that if you look at Wij, W tilde, Ij is equal to W exponential Uj minus Ui, then that's a simple, in fact, that's a simple proof. That's a simple computation by change of variable. It's again independent. Okay, if you suppose that divergence is equal to 0, so we take H is equal to 0 now. So if you suppose that the divergence of the weight is equal to 0, and that's critical to prove that, then in this case, this W tilde, it's again gamma. And then the strategy is the following, is that so instead of looking at the initial Dirichlet law, you look at omega tilde. Okay, so you look at this omega tilde, which is constructed from this extra randomness, and then you condition on W and on some beta, which are related to Margarita's talk, and you make some computation and you can make restriction on that.
So if you recall all technical
Yeah, okay.
details from Margarita's talk of yesterday, then you will understand
I'm sorry,
the
I
next minute everything. Thank you.
Sorry for me.